Every curve has a secret. At every single point along it, there's a hidden number that tells you exactly how steep it is, which direction it's heading, and whether it's about to peak or plummet. That number is the derivative. And once you understand it, you don't just pass your exam for A-level maths. You see maths completely different. I'm going to show you something that, towards the end of this video, connects everything. A single idea that links gradients, tangent lines, turning points, all of it. But we need to build up to it, so don't skip ahead. In this video, I'm going to take you through the entire foundation of differentiation for Edexcel Maths, from the ground up. So therefore, we're going to be covering 4 sections. 1. What differentiation actually is. First principles, the limit definition, and why it works. 2. The rules that make it fast. So you have the power rule, constants, sums, differences. 3. Differentiating everything else. Things like exponentials, trig, and lin x. And 4. Using that knowledge. So tangents, normals, stationary points, and curve sketching. By the end of this, you will have a complete toolkit. So let's get into it. Alright, so imagine you are hiking up a mountain. At any given moment, you could ask yourself, how steep is it right here? Like right under my feet. Not the average steepness of the last kilometer, not the steepness of the whole mountain, just right here, right now. That question, how steep is this curve at a single point, is exactly what differentiation answers for us. So let's formalize this. Take a curve y is equal to f of x, and let's pick a point at x, and another point just a small distance away at x plus h. If we draw a straight line through those 2 points, that's called a secant line, and its gradient is f of x plus h minus f of x over h. That makes sense, it's just rise over run. Nothing fancy. But here's the question. What happens as we make h smaller and smaller? As h shrinks towards 0, the secant line gets closer and closer to a line that just touches the curve at that point. That line is the tangent, and the gradient of the tangent is what we call the derivative. So in notational form, we can say that f dash of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. That right there is differentiation from first principles. Now realistically, it's very rare you'll actually use this formula in actual exam calculations. Why? Because they're much faster methods that I'll show you now. But however, understanding why this works is often what separates students who get an A from students who get an A star. So let me show you a quick example so this isn't as abstract. Let's say we have to differentiate f of x is equal to x squared from first principles. Okay, we can say that f dash of x is equal to the limit as h approaches 0 of x plus h squared minus x squared over h. And therefore, if we expand the numerator then, we get the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over h. From here now, the x squared terms cancel, which means that we get the limit as h approaches 0 of 2xh plus h squared over h. Okay, now from here we can factor our h, which means that we get the limit as h approaches 0 of 2x plus h. And finally, as h approaches 0, we can say that f dash of x is going to equal 2x. So as a result, the derivative of x squared is 2x. Okay, now at x equals 3, the gradient is 6. At x equals negative 1, the gradient is, well, negative 2. So the derivative gives you a gradient function, which is a formula that tells you the steepness at any point you choose. Now just a note on notation here, you'll see 2 main forms, f dash of x which is Lagrange notation, and dy by dx, which is Leibniz notation. They mean the same thing, which is the rate of change of y with respect to x. Now, if the first derivative tells you the gradient, the second derivative tells you how the gradient itself is changing. So in other words, it's the rate of change of the rate of change. We'll use this in section 4 to determine the nature of stationary points. So don't just forget about it. Keep it in your back pocket for now, because we'll come back to it later. Alright, so the first principles are foundational, but they are slow. Nobody wants to expand brackets every time they differentiate, okay? So this is where the shortcuts come in. The main shortcut here is the power rule, okay? Because we can say that if y is equal to x to the power of n, then dy by dx is equal to nx to the power of n minus 1. Okay, so all we do here is we bring the power down, we reduce the power by 1. That's it. Okay, that's the most important rule in all of differentiation. Notice that this works for any rational powers, okay? Integers, fractions, negatives, all of them. But now we've got something else to think about, okay? What if we have a constant in front, or what if we have a sum, or just a constant generally? Well, here's what we can do. Constants, okay, they multiply through. So for instance, d dx of a f of x is equal to a times f dash of x. Okay, and if we have a sum, we can differentiate the sum term by term. Okay, so d dx of f of x plus g of x is equal to f dash of x plus g dash of x. And also remember that constants by themselves just vanish. Okay, so d dx of c is just going to equal 0. So here's a pretty simple example. If we have y is equal to 3x to the power 4 minus 5x squared plus 7x minus 2, then we can say that dy by dx, okay, is going to equal to 12x to the power 3 minus 10x plus 7. Why is that? Because remember, each term is handled independently, and the constant negative 2 disappears. Now here's something that the A-level exam loves to do. They'll give you an expression that doesn't look like x to the power of n, but it absolutely is. You just need to rewrite it first. So this is where your understanding of indices comes in. So for instance, y equals 1 over x to the power of 3, we can rewrite that as x to the power of negative 3, which means that dy by dx is going to give us negative 3 times x to the power of negative 4. Meanwhile, if we have y is equal to root x, that's going to give us x to the half, which means that dy by dx is going to equal a half x to the power of negative a half. Lastly, for y is equal to x squared plus 3x minus 5 over 4x to the half, we're going to divide each term first and then differentiate. Okay, so what we get from that is dy by dx is equal to 3 over 8 x to the half plus 3 over 8 x to the minus a half plus 5 over 8 x to the negative 3 over 2. Alright, so now we can differentiate any polynomial or rational expression using just the power rule. But now there's another issue, because what about things like e to the x, sin x, ln x? Those require their own rules. Okay, and it's actually quite simple. Now, one of the most remarkable facts in maths is that d by dx of e to the x is simply just equal to e to the x. So the function e to the x is its own derivative. Okay, the rate at which it grows is equal to its current value, and no other function does this. Now, to put this into perspective, let's imagine we have a population of bacteria, okay? And every single bacteria unit splits into 2 at a rate proportional to how many bacteria there currently is. This means that the more there are, the faster they grow. That's self-reinforcing growth, and that's e to the x. To represent this generally, we'd say that d dx of e to the kx is equal to ke kx, okay? So the chain rule is technically at play here, and we'll cover that properly in part 2, but for now just remember the coefficient of x comes out front, Okay, now for trigonometric functions, we know that d dx of sine x is equal to cosine x. And meanwhile, d dx of cosine x is equal to negative sine x. Okay, the key thing to remember here is the fact that the d dx of cosine x is equal to negative sine x, because this is often a classic mistake that you can trip up on. A good way to intuitively remember this and understand it is the fact that differentiation cycles through trig functions, okay, with a sign change every 2 steps. So for instance, we have sine x at the beginning, we differentiate it, we get cosine x. Differentiate that, we get negative sine x. We go again, we get negative cosine x, and then we get back to sine x, okay, so we've got a cycle there. Now with the coefficient, we can say that d dx of sine kx, okay, is going to equal k cos kx, right? And d dx of cos kx is equal to negative k sine kx. And then for tan x, we can say that d dx tan x is equal to sec squared x. Now for ln x, we can just say that d dx of ln x is simply equal to 1 over x. The way to think of this is think of ln x as a function that grows, but it just keeps getting lazier each time. It rises forever, but it gets slower and slower. And so therefore its derivative, 1 over x, captures exactly that. It's a shrinking rate of change. Okay, so now we have a complete toolbox of derivatives. We have the power rule, exponentials, trig, logs, but knowing how to differentiate is only half the story. The real question is, what can you actually do with a derivative? And that's what this final section is about, and this is where the marks actually are. Okay, so now you already know the equation of a straight line. Okay, that is y minus y1 is equal to m times x minus x1. So when the exam asks you to find the equation of the tangent to a curve at a point, all you're doing is 1, differentiating to get dy by the x. 2, you then plug in the x value to find the gradient m, and then 3, you use that point and m in the straight line equation. It's very simple. But what isn't simple, of course, is doing this all under exam style conditions, which is why, guys, if you're struggling with those exam style questions and exam style prep, make sure to check out the community. As you can see, a student of ours, they did one of the worksheets and she got 100% in a test. Okay, so yeah, if you're struggling with exam prep and you don't know where to start, and you feel like you know what you're doing, but for some reason you're just never approaching the A or A star, make sure to check out the link below. But anyways, back to the explanation. Alright guys, so let's do a quick example here. Let's say that we need to find the equation of the tangent to y is equal to x cubed minus 2x plus 1 at x equals 1. Okay, we're told that dy by dx is equal to 3x squared minus 2. So therefore at x equals 1, we can say that m is equal to 3 times 1 squared minus 2 is equal to 1. Therefore we can say that the point y is equal to 1 minus 2 plus 1 is equal to 0. So therefore we get 1, 0 as our point. As a result, y minus 0 is equal to 1 times x minus 1, which means that y is equal to x minus 1. For the normal, all you have to do is flip the gradient and change the sign. Okay, so therefore the m of our normal is going to equal negative 1 over m tangent, which means that our final answer here, guys, is going to equal y is equal to negative x plus 1. So let's go back to our hiking situation again. A stationary point now. A stationary point is the top of the hill or the bottom of the valley. It's the brief moment where the ground is perfectly flat beneath your feet. You're not going up and you're not going down. You're stationary. So in other words, a stationary point is where the gradient is equal to 0. In other words, f dash of x is equal to 0. But there are 3 types of stationary points. We have a maximum where the curve goes up, flattens, and then comes back down. We have a minimum where the curve goes down, flattens, and then comes back up. And then we have a point of inflection where the curve flattens but it doesn't change direction. So, remember the second derivative from earlier? Well, here's where it pays off. At a stationary point where f dash of x is equal to 0, if f dash dash of x is bigger than 0, it's a minimum. Why? Because the curve is concave up. a bowl. When f dash dash of x is smaller than 0, we have a maximum. Okay, the curve is concave down like a hill. And when f dash dash of x is equal to 0, well, that's just inconclusive. Okay, this could be a maximum, a minimum, or just a point of inflection. So let's say we have to find the stationary points of y is equal to 2x cubed minus 3x squared minus 12x plus 5 and determine its nature. Step 1 here is to differentiate it. So we get dy by dx is equal to 6x squared minus 6x minus 12. Step 2 is to set it equal to 0. Okay, so 6x squared minus 6x minus 12 is equal to 0, which means therefore that x squared minus x minus 2 is equal to 0, which means we get x is equal to 2 or x is equal to negative 1. But we're not done yet. Step 3 is to find the y values. Okay, so at x equals 2, y is going to equal 16 minus 12 minus 24 plus 5, which equals negative 15. So therefore we have a point of 2 minus 15. Okay, and at x equals minus 1, y is equal to minus 2 minus 3 plus 12 plus 5, which equals 12. So therefore we have another point of negative 1, 12. Remember, we're not done yet because they aren't wanted us to determine its nature. So how do we do this? Well, that's the second derivative test, remember? Because now what we're going to say is, well, look, d squared y over dx squared is equal to 12x minus 6, which means that at x equals 2, okay, f dash dash of 2 is equal to 18, which is greater than 0, so therefore we have a minimum. Meanwhile, at x equals negative 1, f dash dash of minus 1 is equal to negative 18. Obviously, it's smaller than 0, which means we have a maximum. And linking to this, what do we do now if the exam asks us to identify whether a function is increasing or whether it's decreasing? Well, this is actually quite easy. Remember, it's all about the gradient. So if f dash of x is greater than 0, our function is obviously going to be increasing, and the inverse of that is true. So therefore, when the exam asks you to sketch the gradient function from a given graph, we know now that stationary points in f of x become zeros on f dash of x. Okay, and where f is increasing, the derivative is above the x-axis, and where f is decreasing, the derivative is below the x-axis. But we're not done yet, guys, because in part 2, we're going to be tackling the product rule, quotient rule, chain rule, implicit differentiation, parametric differentiation, connected rates to change, and differential equations. So that's where differentiation gets really, really powerful. But even just before that, guys, there's another issue here, and that is the fact that exams are about 30 days away. So therefore, if you don't know how to revise, make sure to watch the video below, because that's a classic issue where you need to mark and it's taking a long time. So what I've produced for you guys is a free mark tool that you can use to mark your papers instantly. So with that done, have a good one, guys, and best of luck.